Hi, Benedikt.
Hi Matthias, how are things? All good?
Thanks, yeah.
So this is getting a bit too complicated, so I thought I'd just call you. Maybe we can try to come up with a formal setting to make sure that we can agree on something no matter when and where the messages are delivered.
Sure. This sounds like a synthesis problem, huh? We need a distributed strategy, one local strategy for each of us that allows us to satisfy a specification, something like reserve a tennis court only once independently of what the uncontrollable environment does with our messages. How about the following setup? There are two processes which proceed in synchronous rounds. In each round, both processes get an input, not necessarily the same, from a fixed finite set, and each of them produces an output again from a finite set.
Yeah, this sounds good, but I think a lot of work has already been done in this area.
That is true. The setting from literature could be classified according to whether the communication link is static or dynamic. I think we are looking for dynamic links.
Yes. Moreover, messages may be from a finite set or transmit the whole unbounded knowledge of the process so that they are unbounded. So let's go for a dynamic network setting with a causal memory. But how do we formalize this?
Let's assume a network model N, which may include up to 4 different communication graphs. The graph tells us whether both messages are delivered or only the one sent from process 2 to 1 and so on. In the worst case, none of them is delivered. In every round, the uncontrollable environment not only chooses the inputs, but also the communication graph.
Okay, I see. And let's say that a process can at least see whether its message was delivered in that round or not.
Yes.
But now, what exactly is transmitted depending on the communication graph?
Well, as we assume causal memory, a process broadcasts everything it knows about the history of a computation. For example, if the communication graph is empty, then process 1 and process 2 only receive their own input. Now suppose that the message, the input bit sent from 1 to 2 gets lost, but the one sent from 2 to 1 is successfully delivered. In one go, process 1 will know the whole history of inputs seen by process 2 so far. This is actually illustrated by the green shaded area. And depending on the knowledge, a process produces an output. A function mapping such a causal memory to an output is called a local strategy, and a pair of such strategies finally gives rise to a distributed algorithm.
Okay, I see. And in the case displayed on this slide, the second process will be aware that its message was delivered. But as the other message gets lost, its knowledge grows only by its local input bit.
Exactly.
Now, what is the decision problem we are looking at?
Let's take as a specification language LTL and assume that it can talk about everything: inputs, communication graphs, and outputs. This would allow us to say that a property needs to be verified only if both processes hear from one another infinitely often. The question is then whether for a given formula we can come up with a distributed algorithm such that no matter what the sequence of inputs and communication graphs is, this sequence along with the corresponding output satisfies the formula.
Nice. Shall we look at some examples?
Good idea.
So let's agree on a set of formulas and then sync via instant messenger.
Okay, see you.
Bye. Okay, so here we assume that in each round, exactly one of the links is broken, and that inputs and outputs are bits. The first formula, phi1, says that in each round both processes output the same bit. Well, if both processes agree that they always output 1, then this should work, right? So let me propose this to Matthias. Here we go. I'm process 1 and Matthias process 2. Let's see what happens when we have this input. The communication graph is from right to left, that is, I can see the input of process 2, but the strategy says to output 1 anyway. With this input signal, I can only see my own input, but I'm aware that process 2 also knows it. And I output 1, of course. Similarly, with these communication graphs, I do not see the other bit. But now it's going to be interesting. With this communication graph, I will not only receive the most recent bit, but all bits that I may have missed before. This is what is called the causal memory. And so on. Now, if Matthias respects the strategy, then the specification will of course be satisfied, no matter what the environment does. Okay, now we have an additional requirement, namely that we both output 1 infinitely often, if and only if both inputs are simultaneously 1 infinitely often. So the previous strategy does not work anymore, obviously. But wait, is there any strategy at all? Okay, so this is what I thought. Now we suppose that the very same property, that is the conjunction of phi1 and phi2, holds if the environment provides both links infinitely often. That is, both processes have complete information about the whole history infinitely often. But still, this doesn't seem so obvious, does it? Okay, I see. These blocks are finite size. So if there are infinitely many input pairs 1, 1, then we output infinitely often 1 and 1. And if we output 1 and 1 infinitely often, then by definition of our strategy, this means that there are infinitely many blocks containing an input pair 1, 1. Let's try this. So for this input signal, there is no preceding block. By default, I output 0. In the second input signal, the link has changed. So the preceding block is entirely in my causal memory. However, there is no input pair 1, 1, so I output 0. The next two signals do not change the link, so I output 0. And by the way, I cannot see the input bit of process 2. But now the link changes again, and the entire preceding block is in my causal memory. That is, all its bits become visible. In this block, there is an input pair 1, 1. So I output 1. The next link is the same, so nothing happens. But then we have a new link, and it turns out that in the preceding block there is a pair 1, 1, so the output is 1. Now, if Matthias also respects this strategy, the overall outcome will satisfy the formula.
Hi, Benedikt.
Hi Matthias, the strategy works. The question is of course whether we can decide whether for a given formula there is such a strategy.
In fact, we already know that the problem is undecidable if the network model contains the empty link. This is actually to Nathalie and Rosner.
Okay, then let's try to show decidability for all network models that do not contain the empty link.
Yes, let's go. We can show it for a simple network model first, where the first process is always fully informed, but the second process may be lagging behind. It turns out that if there is a distributed algorithm, then there is also one with finite memory, that is, where a process needs to remember only some bounded abstraction of its causal memory. Then we are actually in a well-studied decidable setting where two players, one with perfect and one with imperfect information, play against an uncontrollable environment. Afterwards, we reduce all other cases of network models to this case using a simulation technique. Essentially, the first process always simulates the more informed process. For the rest of the presentation, let us focus on the reduction to finite memory.
The main idea is to employ a tree automaton with a Rabin acceptance condition that accepts exactly the distributed algorithms, that is, pairs of local strategies that realize a given formula. To do so, we need, of course, a suitable encoding of distributed algorithms as trees. Intuitively, every node corresponds to a possible history, that is, a sequence of input signals and communication graphs that the system was exposed to so far. Moreover, we have one child node for every possible extension until the next synchronization of processes, that is, for every possible sequence starting with a synchronizing graph and having right-to-left links otherwise. Thus, this tree has infinite out degree. Nodes, that is, histories, are labeled with pairs of trees, tree 1 and tree 2, which represent partial local strategies. Tree 1 is the local strategy for process 1, given the corresponding history. For every possible continuation right before the next synchronization point, it specifies a local output, depicted in the circles with a red frame. Similarly, tree 2 is the local strategy for process 2. For every possible continuation right before the next synchronization point, it specifies a local output. However, note that in this case, process 2 does not see process 1's inputs, indicated by the question mark, so that the out degree of tree 2 is smaller than that of tree 1. So we note that a distributed algorithm is represented by an infinite tree with infinite branching and infinitely many node labels. Now, to determine the outputs of both processes given a sequence of inputs and communication graphs, we look at the green node that corresponds to the history seen so far, up to the position right before the last synchronization point, and then look at the red nodes in the attached tree to find the corresponding local outputs. As long as in the system execution we have communication links from right to left, we just go further down in the red tree to determine the local outputs. But when we see another synchronization link, we go further down in the green tree and discover the corresponding outputs in the red trees, namely at a child of the root. Again, as long as we have communication links from right to left, we just go further down in the red trees to reveal the local outputs. Now, there is a Rabin tree automaton accepting such an infinite green tree if and only if the tree represents a distributed algorithm realizing the formula. Well, this tree automaton is essentially derived from a Rabin word automaton extracted from the given LTL formula. The tree automaton may have infinitely many transitions, but it has only finitely many states, and this is what finally allows us to show that if some tree, that is a distributed algorithm realizing the formula, is accepted by the Rabin tree automaton, then also one that is, in a sense, regular. Its subtrees depend only on the current state of the tree automaton. In other words, the decisions of the corresponding distributed algorithm only depend on the bounded abstraction of the past. As already mentioned, this finally allows for a reduction to a well-studied game to determine whether a distributed algorithm realizing the formula exists at all. The other building blocks of the proof can be found in the paper, which is available on arXiv.